Let me share my screen. Is my screen visible?
Yeah.
Yeah.
Okay, let's start. So we'll start from as usual from the assignment, and then we'll go to the a few doubts asked by Arunot Paul in Griffith's book.
Sorry. What are the
Yes.
doubts?
Uh,
I joined late.
no, the doubts we have not discussed yet.
Okay.
We'll
Okay.
come to that at the end, and it's a
Okay.
pretty easy, so we can all grasp it. Okay.
Okay.
So do you have any particular doubt from this previous week? The assignment,
No.
variation theorem, or anything?
Yeah. Assignment. There was that for a rotor, which are the other possible
Yes.
uh,
Yes.
allowed wave functions?
Harmonic oscillator, not the rotor, I guess. Huh?
Yeah.
Is it? Using this one, no?
Yeah. Harmonic
Harmonic
oscillator.
oscillator.
Correct.
Yes, the
Correct.
fine.
Correct.
Yes, yes.
Huh.
No, not this question. It's question number four, I guess. Yes. Yes.
Question number 4. Yes.
Yes. So, okay, then let us do that one first. So, see here in variational theorem, what we are trying to do, that we are trying to guess one wave function, right? The phi
Hmm.
is the guess wave function. So, our guess should be our.
1 second. I just logged in from the other. I will log out from here.
Okay.
One second. Yeah. Sorry. Huh.
Yes. So the phi, the trial wave function, is usually a this is a trial wave function, but as a trial wave function, also it has to be some meaning. Means we are guessing it because of we have that has some specific property, right? So if you see that cos lambda x, this thing has been declared. Cos lambda is a trigonometric equation, right?
Yeah.
Function. So
Yeah.
here also, actually the question actually asking that what other trial wave function we can take to start with.
Hmm.
It may change. The wave function may change at the end. Means when we are will vary the variational parameter. So here, as you can see, in all the cases, lambda is the variation parameter only. Right?
Hmm.
There are no other variational parameter. But in harmonic oscillator, we also know that it has to be symmetric, right? Some
Yeah.
symmetry has to be there. So
Yes.
if you find the option, that you can see that e to the power lambda x square, that will give you a parabolic kind of
Really?
wave
I thought
function.
it gives a incremental, like it increases exponentially.
Yes, but then it is a trial wave function, right? So lambda value should be such that, means we will vary the lambda parameter at such a way that it will be a means eventually the wave function will be a, or the energy will be a valid wave function, right? So cos lambda x, this thing also doesn't end, right? But means the lambda parameter, lambda is the variational parameter, yeah. So
Hmm.
when we will introduce, means vary the variational parameter and check the energy at each step, we will see that at maybe at certain value of lambda, the energy will be close to the system. Maybe the
What I
physical.
thought was, you know, uh, for this, the wave function should vanish at both
Hmm,
the boundaries.
hmm. So,
Uh,
so my see that phi is not really here. Means the it is a, we are just a lambda x square. This is just a trial wave function.
yeah.
This is not a, means we are saying this will be a valid wave function at the end, right? We don't know yet.
But means from what I have studied,
Hmm.
that in variation theorem, you can take any function as a trial wave function as
Yes.
long as it obeys the basic boundary condition.
Yes.
Then, depending on how good your guess is, your energy will be either close to the real energy or it might be very far
Okay,
also.
okay. I understand your doubt, and you are. I think you are correct. Here, I think I am also wrong here. So the maybe the option should be e to the power minus lambda x square, right? A
Yeah,
Gaussian
it,
wave
We
function.
can take lambda as negative also while
Yeah,
we are
that
varying lambda.
yeah, but then the wave function doesn't vanish at both the ends.
infinity you are saying.
Well, if it is e to the power minus x square by 2, then it's basically a Gaussian.
E to the power minus x square, or
X square by 2,
e to the
suppose.
power x square by 2 will be the Gaussian. or a
Yeah, yeah. E
parabolic.
raised
It
to
will
minus
keep
ax square
increasing.
is your Gaussian function.
Yeah, if the
That
lambda
is
is a,
valid. That is
yeah,
valid.
yes.
But
Means you are
plus,
saying if lambda is negative here, then it is valid.
yes.
Yes. So maybe when we will solve this thing, maybe when we'll, I don't know, whatever the trial wave function is. So if we can solve the energy for it and do the differentiation with respect to the lambda, maybe
Hmm.
we will find that lambda value is negative. It is
But
possible.
what I understand is suppose this my phi is equal to e raised to lambda x square.
Hmm, hmm, hmm,
I am going to vary lambda.
hmm.
But before I start varying lambda, x is a component that I know.
Yes.
So x, let's say, can vary from minus infinity to plus infinity.
X is already varying. Yes.
Yes. So x is, I know the x value, they are at the boundaries. When you
Hmm,
take a harmonic oscillator, your x
hmm.
cannot be out of that parabolic curve.
Yes.
So the
It should be
boundaries of
inside.
that parabolic curve is your limit for your values of x.
Yes.
So even if we don't know what those values are, if we take minus infinity to plus infinity, that basically covers everything.
Yes, e to the power plus.
So
Actually, I guess you are correct. Maybe we should have gone for e to the power minus lambda x square, right? Arunotpal,
yeah,
what do you
no,
think?
if it is minus, then it is fine
Yeah,
because
yeah. That's what I am saying. That if it
uh,
is minus lambda x square, then it
that
would be
will vanish.
yeah, it will vanish at minus infinity as well as plus
Yes,
infinity,
yes, but
and it will have a valid at x is equal to 0 also.
yes, but
Yes,
e raised to lambda x square doesn't vanish.
yes. And the
So
boundary
basically, we
conditions
have
are.
two properties. One is it should be symmetric with
Hmm,
respect to the half point,
hmm.
and the second thing is it should vanish at the boundary point.
Okay, okay. Yeah, you are correct.
So because we got this lambda x square as the correct answer.
Hmm, hmm, hmm.
Actually, my answer is none of the above, but
Understood.
there was
Yes.
none of the above, so I clicked on any one of them.
Okay.
So, but that one of them was not right. But
Okay.
this is what I thought, that none of the answers are correct.
Okay. Okay. Yes, I will. I'll then I will send it for a recheck or the re-evaluation so that all of you are getting the marks for it. Before that, I will once discuss with professor if during the variational means if we can vary the value of lambda in such a way that lambda is negative, something like that. I will just once check with
Yeah,
him.
yeah, sure.
But I think I think you are correct. What your point is? What do you think, Arunatpal?
I think lambda can come as negative if we are like trying to find a minima and differentiating it. Then we may find that lambda is a negative value.
Hmm.
And also, like this specifies for a harmonic oscillator.
Hmm.
And while we plotted the psi ends for harmonic oscillator,
Hmm.
uh, the solutions doesn't exactly become zero at the boundary of that parabola.
No, it will not end at the boundary, but I think yeah, Avinash was talking about the plus minus infinity. Means he was not talking about the boundary, because the potential was finite. So eventually some leakage was there.
Tunneling
Means
will be
the
there.
tunneling was there.
Yeah.
So at the
But if you
I
take
think he is talking
infinity
about the
and minus
infinity
infinity,
condition.
it should vanish
Hmm. It is
for
possible.
all values of lambda.
Yes, yes.
Means
Good,
we cannot
good
put,
question.
if lambda is this only, then this will be valid.
Hmm. Hmm, hmm.
I don't know.
Maybe close to the energy. I'll check that. I'll check that
Yeah.
and
Yes.
I'll come back
Yeah.
to. Okay. And I think rest of the questions are pretty much thing.
Uh,
So let
there
us.
is a there's
Okay.
an assign question in the next assignment.
Okay. Yes. Yes. In the next assignment, there are some questions from this. Maybe from variational theorem,
No, no,
or
but that can you just go back or next question, next one. This
acha.
one. This no, no, number 5.
Yes. Yes.
Using cos lambda x is equal to trial function, the energy
Hmm.
given for this is this much, and what is the value of A?
Huh.
We solved this and we got the answer.
Yes.
In the next assignment, which we are supposed to submit tomorrow,
Yes.
same question is there without the trial function.
Is it so?
Yeah, it says using a trial function, and rest is exactly the same. Expected value of ground state is this, A is equal to this, the value of A is this much.
Okay, let me once check. Before
Yeah,
that,
The
I will.
question 5.
Acha, I'll check that at the end. Huh? I'll check
yeah,
that.
yeah.
I'll come back to that. Acha, maybe some mistake was done. Okay, I'll check that. Okay. Anything else from the lectures or the assignments?
I
No.
have two doubts, like from perturbation theory actually. One was regarding that question 7,
Yeah, that we solved.
and
I think you did
yeah,
you
I
check that?
checked the video. I
Okay.
had doubt like when you are putting psi k one first
Hmm.
inside that inner product.
Acha, let me check that presentation file. I have that. I also don't remember it now. Is it the question? Yes. Yes. Here, right?
Yeah, this one.
Yeah.
So when you are putting psi k1 in place of inside the inner product of e12 e1 second, sorry.
Here.
Yeah,
Acha, you
uh,
can't see my cursor. Okay, let me change it.
I can see
yeah,
the
I can
question.
see.
I can see.
This one, right?
Yes.
Yes. Yeah, tell me.
Uh, so how are we? I mean, taking that denominator under everything and uh, making it two inner products over in at the numerator.
So, see, already, let me also check one. So, this EK2, that is the second order correction to the energy, already has the form of like this, right? That psi k
Yes.
naught, that perturbation, psi k1,
Yeah.
according to that our previous knowledge.
Yeah.
So here what I am trying to do, what I have done, that we are putting the value of the expression of psi k1, right?
Yes. Yeah.
Which already have the form of that Cjk and psi j not, or the zeroth order corrected form. So it is like, so from here I went to this line, that uh, that this let me uh, change my color of this pen once, if I can. Let me put black. So what I have done, that here I am putting the value of uh, again the psi k1, right? So and that is psi k1 value is this.
Yeah.
Okay. So now here I am writing again this thing, that kth ek second order correction to the energy is now. This can come, right, because all these j and k can vary. uh, Here it is the kth, right? Means we are varying. You can see like that, we are varying only the j here, which is not k, means we are not varying the k. Here we are varying the j. So, and here only k was there, psi k zeroth, right? Means the psi k proper zeroth order correction to that wave function. So now this summation is there, j not is equal to k. Now this part is there, this psi j zeroth order correction to the wave function, then v, then psi k naught, that is there. That is the first thing. And the second term is that psi k naught was there, no? Psi k zeroth order correction to the energy, that wave function, that is there. And again this v was left, right? This v. So this I have kept here, and this psi j naught at the kth function, that I have ended it like that. So it is again a bracket function, and similarly this thing was there. Should I write it once again? or do you still have some doubt? Okay, let me write it again. Maybe while writing, you can tell me that where is your particular problem is there. Okay. So what we already have, like, let me also check one. So I get one. This is
Summation CJK.
CJK where J not is equal to K, and psi J
Zero.
0, right? Am I
Yeah.
writing it correctly? Yes.
Yeah.
Now you can think of like it is in a Kate function. You can think, right? So it will not change the thing. Will it change? No, right?
No.
So then I'm currently not writing. I'm not expanding the CJK. I will expand it later, so it will help. So then our energy correction of the kth n is equal to k, and that is the second order correction will be
So psi k of zero
psi
order
k of 0. Let me write it also like same k. Then there will be some
v.
v is there. That is the perturbation.
Yeah. Then
Then it
psi
will
k
be
one.
1n, right?
Yeah. Psi k
It is
first.
like that. Now I will put this value of here. So it is like uh, psi k 0. These are all actually integrals, right? So that's why we can separate it like that way. Suppose this is here j not is equal to k c j k. Uh, we can write psi j not, right, like this.
Yeah.
No, right now
There's no
no
denominator.
denominator is there.
Hmm.
Okay. Now we are just expanding this thing. So we already know that what is CJK. That CJK was we found out that uh, am I making any mistake or no? Right? Did I? I am not sure.
No.
Uh,
So far it's all right.
so no, I am just saying that if I have made some mistake here, that CJK there is no J not is equal to K term should be there or not. You can check it from the lecture once. We are just currently putting the value of this. So this is a part of in the inside the integrals, right? So I
Hmm.
am just what I am trying to do. That's if I write it like that, let me write one. What was the value? I forgot. This I is 0. Then
V.
V
Then psi k zero.
psi k is 0. It is Ng, and then there is some numerator, right?
Yeah.
Denominator.
Denominator,
Denominator.
sorry. E
E k zero minus e j zero.
E J 0. Right, and there is this ij zeroth is there.
Yeah. From here I got confused, like how to manage these two inner
So this is all
products.
multiplication, right? This is all inside the multiplication.
Yeah.
So what I have done that I have taken the summation term out. So k is not a variable here. J is the variable. So before that there is no j, right? So only j can vary. So we can take this summation outside, and then it is just a multiplicative term. That suppose I am writing this thing first, I j naught b psi k naught, and in denominator there is this thing, right? Ek naught minus ej naught, and this thing is as it is the previous thing, ek naught v psi j naught. Not means it is not a not means it is zeroth
Zero.
order
Yeah.
correction here.
Important.
Yes. So as it is the denominator is, we can write it all over it, right? It is a means we are just multiplying the integrals. These are integrals and we are multiplying this. So, and this is I don't think it will it should be it can be under both of them, right? It is not like that I can take under this. So then we have taken the Hermitian property of that and of this operator and go into the next step, right?
Oh, okay. Yeah, I was thinking like if we have to consider like V is operating on the kit vector on the right, and then we have to do something like that. That's why I got confused.
Hmm. Okay, okay.
Okay, okay. After that, I could do the calculation.
Hmm. Okay.
And I had one doubt regarding the derivation sir showed us in the lecture. Uh,
Okay.
we started with an operator A
Hmm.
operating on a function f.
Which lecture you can you tell me?
The first lecture, first I think it was
The
second lecture
turnover
was.
rule where derivation is there.
Okay, the turnover rule that was also I think we have discussed, right?
Yeah, I know.
Yeah, but yeah, my doubt was actually different one.
Okay. I'll go there. Okay, let me check PDF. Did you one thing that did you find this PDF folder there? We have
Yeah, yeah,
shared these
yeah.
slides with you. Okay. So this is the pattern machine thing. If I go to find it here, here means
Yeah,
Here.
this.
yeah.
F is an eigenfunction of A.
Hmm.
We are starting with that assumption.
Okay.
So G is also another eigenfunction of A.
Yes.
And then we are writing that psi star A operating on psi d tau is equal to the thing that we
Where are
have
we?
started.
Psi star operating on.
Psi star A operating
Hmm.
on psi is
Yes.
equal to integration of psi A of
Yes.
A psi that thing. So
Huh.
psi is also another eigenfunction of A, right?
Yes.
So
It should be right. It should be or it may not be. Let me also check. Did Sir also I think during solve
yeah,
when
I
he
think
solved this?
like some assumption is missing.
I
Like
didn't understand the question on this. Sorry, can
Anupam, can you repeat? Till then I am
yeah,
finding this
my
thing.
question was like f and g are both eigenfunctions of A,
correct.
and next we took psi as a linear combination of those two eigenfunctions.
Hmm.
So my question was, do we have to assume that f and g both have same eigenvalues? Otherwise, how can be psi also another eigenfunction?
Okay, let me go to that particular lecture. Okay, here
T
you
divided by S.
think he was also writing that.
Yeah, this one.
Yes. Psi A star. Then he write it like that. Yes. Then let us hear what he's saying.
What will it be?
Can you hear?
It
You
will
can tell
be
me. Can you hear that?
C1 multiplied by
No,
A hat
no.
F star.
No.
Okay, you can't hear. Okay, that will be another problem. Acha. Acha, let me share it like that way so that you can hear. Let me stop presenting. Go to a particular tab. Now I guess you can hear. You tell me, na? Now if you
A
can,
hat F plus C2
Yeah.
multiplied by
and now you can hear. Okay, we'll just go to.
C2G multiplied by A hat operating on C1F plus C2G full star d tau. Right, d tau. Okay, and then what we do is we expand this. That is the step that I want to skip.
Oh.
It's not all that difficult also because A hat operating on this
Yeah,
linear
after
sum.
that,
What will it be?
there was
It,
not anything.
Yes, so he has keep that part. But as you can see, if suppose let me write it there also. Can I write in that particular PDF? I don't think so. Okay. Okay, let us discuss only from this video part. As you can see, now A is going to operate on uh, CF. Acha, there is a
Conjugate.
conjugate is there, but what if, so if we are not thinking about the conjugate, let us also try it ourselves here. Suppose here I am going to write mm, so let me write it. So we already know that uh, suppose A is the operator and psi is the wave function, we are getting
I think
something.
you need to change the share.
Yeah,
Screen
sorry.
froze.
Yes. Thank you. Yes. Now I think you're able to see what I'm writing. So I was saying like this. So the, if A operator is working on the psi and giving us, suppose we are not writing it, we are writing it F, right? We're
Hmm.
talking F, and suppose A is also working on
G.
G, we are
G,
getting something
B. BG.
B
BG.
in BG, right?
Hmm.
Now we are saying that psi is another wave function where it
It
is
is a linear
C1.
C1
combination of F and G.
F plus C2 G.
So by definition, it should have been uh, uh, psi should be an eigenfunction of A, right? Because if A is working on psi, then A is working on C1F plus
C2.
C2G, right?
I
Hmm.
mean, like, this is what I am asking that shouldn't we assume that for F and G, the eigenvalues should be same?
Eigenvalues,
Yeah,
yes,
like
or
in the
else
both cases should
else
be
I
same.
can't, make the next step. Actually, I think I
Yeah,
have shared one tutorial problem. I think tutorial one, I guess. If you see, I have shared that CH107 tutorial problems, right? In one of the problem was like that. Do you remember?
Means
yeah.
why the eigenvalue should be the same? The
Let me show you. Let me show you here what I am trying to say. So it will be C1,
C1A
acha, C1, and
AF
then AF
uh, plus
plus
C2 C2 BG.
C2 C2BG.
Uh,
Now see that we can't take common of anything, so that C1F plus C2G is there. If A is equal to B, then only if F is equal to B, then we could have taken A common,
And
uh,
C1F
C1F plus C2G. Then
A
it
psi
A psi, right? It would have been a case like this. Then the psi would have been a
Eigenfunction.
eigenfunction
eigenfunction.
of A. So is it really required when we are trying to solve that specific part?
Yeah, otherwise, how can we write that psi star A psi
Hmm.
d tau is equal to integration of psi A psi whole conjugate d tau?
Okay, let me also. I have to check that. And then let us also write that thing. Why we can write it here. Let us check. You guys can see my screen, right?
Yeah.
Yeah.
Okay. So I'll try to write that. So we already know that psi is C1A plus C2G,
C2G.
and what we are trying to do that psi star, what we are trying to do here to check that. Actually, let me also check what we are trying to do. I forgot. We have to see that if G, acha, we have to take both the side, one like psi star A G and one of these. Then we have to compare both the sides, right? Okay. Mm, okay. So psi star A psi will be like look like that. C1A plus C2G. A is the operator. C1A plus C2G. It is like that, right? And I guess okay. Now it is like that. And there is some integral signs there, and as we are writing it, some dx or something will be something like that is there.
D
Suppose d tau maybe, yeah, we can write d tau. And if it is a Hermitian, then what we are expecting is that this will be a psi a psi whole star, right? Something like that will come, right?
Yeah.
So what this is the LHA left hand side, and what is the right hand side? C1A plus C2G.
Mm.
Now A and C1A plus C2G, and whole is this. This is the right hand side. Is it making any sense what we are trying to do? Uh, so is it necessary that so Urvakpal, do you think is it necessary to psi become a eigenfunction of A?
Yeah,
That
because we started by saying that those LHS equal to RHS.
hmm.
So if psi is not an eigenfunction, how can we say that? I mean, for the derivation, we first showed that uh, f star AF is equal to f AF whole star
Hmm.
integration on both sides are
Hmm.
equal
Hmm.
because f was an eigenfunction.
Yes, yes, yes,
In
true,
that
true.
expression, we put psi.
Yes, true.
So that's where I got stuck.
Here you are saying that AF,
Yeah,
then we can take the AF value so that this is becoming like that. Yes, I guess so. Then maybe this assumption has been missed out. But let me show you this thing. We have once done this problem. If I have it, let me check. Uh, this one, two, seven, tutorial 1, 2. See, under what condition, this fourth question, what I am highlighting,
Mhm.
under what condition will a linear combination of two or more eigenfunctions also be an eigenfunction of a quantum mechanical operator A? Right?
yeah,
This we have solved when the eigenvalue will be same for all.
yes.
Yes. So just a quick thing I just wanted to discuss. Maybe I will check this thing once. I will do this. I will expand this thing myself, and I will write in the maybe in the discussion forum or in the next meeting itself. I will clear that one. Okay. And so let us get back to the questions because we will to finish that. Acha, do you have any other doubts on that slide? You told me you have two
No,
doubts,
no.
right? Okay, okay, okay. I think the first
Yeah,
one
I
is
was,
clear, right?
yeah,
Okay, so this thing right now we are saying that yes, psi is a eigenfunction because that is the way we have solved. But I will also try to check. if by expanding that thing what sir was doing in that video, you also try to do that thing by yourself.
Yeah,
The steps.
actually did the derivation myself, and that's when I got stuck. Like I just
Okay.
started from f and g, and then
Okay.
when I came to psi, that's when I got the doubt. Like if it's not an eigenfunction, how can I even start that writing that expression?
No, that expression can be written, but we have to see that while solving that part, while Sir has skipped a few parts, Sir has said na, that I am
Yeah,
skipping a few
because
parts.
no, we have to equate that because the final expression where sir arrived,
Hmm.
we can arrive there once LHS equal to RHS, and we take a term from RHS to LHS and LHS to RHS. Only then the final result will come.
Okay, okay. Well, I'll check once and I'll confirm that thing. Okay, good observation. Yes, so let us, who have not joined it, so for them, let us quickly solve this thing as you have already got right. The D is the correct answer for the first one. For the is a variational theorem, the thing that the average energy will be less than
Yeah.
that, whatever for the trial wave function will be greater than equals to the ground state energy of that. Okay, so the second question, what will be the answer in the variational treatment of a quantum mechanical problem? Which
In
should be the
this,
answer? Hmm?
the first step is to choose a trial function,
Hmm. Yes,
and
that
then
can be. Yes, the second one is the right.
many iterations should be done to get as close as possible.
Yes, so the fourth option is wrong. What about the first option? What do you think?
Not really. Variation theorem, this is not a condition.
Yes, that means that's what I am trying to say. Means
Hmm.
for perturbation theory, it was a condition that it should be a very close in energy to the exactly solvable system. That is not true for the variational theory. Okay, now while proving variational theorem, the trial wave function is expressed the linear combination of wave function and that are
That
necessarily normalized and
orthonormal, so
orthonormal.
orthogonal and normalized.
Yes, for first two, right? First, orthonormal. Yes. Now these we have discussed that we will I will check that with professor also if we can take that lambda value what we can do or we can put it for the re-evaluation. Okay. So question number five, I think you will get the answer from the lecture
Lecture.
videos. I think 1.14 or something was there.
Yes.
Yeah. So you are also saying that this question is also being repeated in the next assignment. That I will also.
Yeah, the same question 5.
Without that
Yeah, like
trial wave function, they didn't
Okay.
even so it's not even a correct answer because without
Yeah,
giving
this
the
is not
trial
given.
wave function,
This is not given.
yeah, so you cannot find a because
Okay.
trial wave function changes, your a value will change.
So that I can
yeah.
check the question once. Acha, where is this? Just this portal is already open. What question is? Acha, question. So this तो you have already ये ना submitted. Assignment A.
It
Yes,
is done.
assignment 8 is the one that you are checking
Yeah,
right
yeah.
now.
This is already been
9 is
submitted.
tomorrow.
Yeah. No, no. I am just my this thing is little bit different from it.
Go from the other account so that we don't see the answer.
No, no. You will not see. You will not see.
Ha,
This answer
Yeah,
ha,
is not
this
there.
one.
ha.
Acha.
There.
This is question number 5.
Using the trial wave function. Acha, acha, acha. Acha, acha. So you, for now, just you take this as the question from the lecture itself. Okay. So try to give it the answer from the lecture itself. I'll send it for re-evaluation. Okay.
Okay.
Okay. Means for others. So you two have joined and you can answer it right now. But whoever not joined, then they can. I'll send it for re-evaluation. Okay. And then we have next thing, right? That is. Okay. So now question number six. For a particle in a box with infinitely large potential barriers at x is equal to 0 and x is equal to a, let a trial wave function be phi of x is equal to f of x and g of x. These already have been I think solved. for this trial wave function to be valid, f x or g of x cannot be. Now, what do you think? What will be the answer?
X plus 3.
X plus 3.
Why?
Because for the other three, we can suppose it's f of x. So
Hmm.
for other three, we can pick a g of x such that that thing like
At boundary, it is
yeah at
0.
Boundary
boundary
vanish.
comes to 0. We can change the function and signs
Hmm.
to make that. But for x plus 3, we can't do that.
Yes, right. So that's why the it will be the means it will be wrong to take x plus 3 as any of f of x. So A is the right answer. Yeah. So next, I have also told in the previous question that it is actually h
It's
square by m. In the lecture videos, it was
H cross.
mistaken. Maybe it
yeah
was discussed
h
as h
cut.
cut square. So that so I think the answer will be something 0.125 something like that, right?
Yeah.
And there are some more terms are there.
Hmm.
Okay. So I think these are all the questions that I think he has asked. A assignment problem was there. Now these are two questions that Arunotpal has asked from the Griffith book. So he has shared the thing in the discussion forum. So I just took the screenshot from there and pasted here. So let me first read out the question and then we'll go. So what is the time? Can anyone tell me? So it is 6:44. We have some 15 minutes of time. Okay. Let us discuss that. So the question says show that E must exceed the minimum value of V of x for every normalizable solution to the time independent Schrodinger equation. Okay, what is the classical analog to this statement? And hint is nothing like the. So for Avinash, I'm simplified this thing. Suppose this thing is given. So this is our time independent Schrodinger equation is given where some potential is or any. Suppose there you don't have to think of a particle in a box or harmonic. So suppose just a system is there for where this thing is defined.
Hmm.
Now it is they are asking that we have to prove that E must exceed means E must be greater than or equal to V of x so that not equal to means E must exceed that E must be greater than V of x so that the psi can be a valid wave function. So for that they have given some hint that they have given us the equation and they have said that start from so we have to prove that E must be greater than V of x so that psi can be acceptable. So the hint is given that start from E not is equal to this V of x or V minimum whatever. Then we have to see what is the psi and second derivative always have the same sign. So I will discuss this here. So we have d2 psi dx square is equal to 2m by h cut square v of x minus e psi. So now, according to the hint, we will go that suppose E is less than V of x, then what could have happened? So in this case, can you tell me what will be the sign of this part? Means without the psi, what is the sign of this part would be
This is negative.
It will be positive.
E. No, E is less than right.
Yeah, so it should be positive.
E is less than. Then this is positive, right?
Yeah.
Okay. Now, you tell me one more thing that what is the
Yeah.
double derivative of a function means? Curvature, right?
Yeah.
Hmm.
Huh. So now see, so when this is positive, now suppose this is, I am plotting something. So this is my psi, suppose y axis, and this is the x. Okay. So now my psi is suppose, and these are all with respect to the x, right? Only. So they are only one dimension. So suppose my psi is positive. Psi is positive. Then what should be the d2 psi x square? What should be the sign of this? as it is
Oh,
positive already,
yeah, positive.
positive. And when psi is negative, then also d2 psi
Will
dx
be
square will be
positive.
negative, negative, because it is positive, right? So if psi is negative, negative positive, the whole term is negative. That is what my d2 psi by dx square is. So d2 psi by dx square is negative when psi is negative. So that is what it is saying. Then psi and its second derivative always have the same sign. So now
Hmm.
we have to argue that such a wave function doesn't exist or cannot be normalized. So as you can see, suppose my now let me now let me draw once more. Suppose this is my thing x and psi of x. Suppose now my psi is positive. So it will have something like that. The curvature is also positive, right? So psi can expand in this positive x direction also and minus x direction also. What I am saying that see it is in the positive part. So psi of x, when psi of x is positive, so this is psi of x, right? And this is x and this is here the negative psi of x will come. So when psi of x is positive, then you see the curvature is positive. And again when psi of x is negative means in this side of the x axis, right? Then the curvature is negative, as we have discussed here, right? When psi is negative, curvature is negative. When psi is positive, curvature is positive. This is what we have discussed. So these all the thing I am discussing also from that one solution manual is there. You can find out. They have also discussed in maybe in a better format. You can check that. But the thing what I am discussing here is the same. So as you can see, so it will not never be zero, or you can see the it is not really normalizable,
Hmm.
right? So
Hmm.
it
Yeah,
is the same thing you are Avinash, you are saying that it is continuously increasing, right? So it not be normalizable according to that Born approximation or Born approximation. So not the Born approximation with that normalization theory. It should
Interpretation.
have been, yes,
One interpretation.
interpretation, right? So it will not be yeah,
Square integrable.
square integrable. Now when E is positive, let us see what will happen. It means the thing what we want to prove, when E is greater than V of x, then you see that suppose this d2 psi by dx square, let me write it again, 2m by h cut square
That
V
will be
of x,
minus now.
it will be right now it will be negative, right?
Correct.
It is negative. Now when psi is positive, our curvature is negative.
Hmm.
Psi by dx square is negative.
Hmm.
And when psi is negative, d2 psi by dx square is positive.
Positive.
Right? So
Hmm.
now it will look like something like that. The psi of x is here. If psi of x is now positive, then now curvature is negative.
Oh, okay.
And when psi is positive and psi is negative, our curvature is like this. So it will eventually come to a certain value when it will be zero, right?
Hmm.
So
yeah,
it will be square integrable.
normalizable. Yeah,
Yes, which was not in the case. For a certain boundary condition will be given.
Hmm.
Let us not go to that part, that it is increasing or something like that. But it is coming to a value when it is zero, right?
Yeah.
Okay, so that's it.
okay.
And that now it will be normalizable when E is greater than V of x. That was we have to prove that, show that E must exceed the minimum value of V of x. That is E is greater than V of x or V minima. Okay, for every normalizable solution to the time independent Schrodinger equation. Actually, this problem is given from the first chapter or the second chapter actually. Since when this perturbation, these all things are not recorded. Only we have to know that what are the quantum mechanical postulates and what is the Schrodinger equation. Just that. We
Yeah,
don't.
it's even before infinite square value.
Yes, yes, yes.
You can say.
But yeah. So this is the first problem. So then, so Avinash, did you get it? And yeah, Arunotpal,
Uh,
did you get it?
yeah, got it.
Okay, okay. The next problem was that show that, so a special case of that previous problem is going to come. Now they are saying so that there is no acceptable solution to the time independent Schrodinger equation for the infinite square wave. So let me write down the Schrodinger equation for the infinite square wave potential, that d2 psi by dx square is equal to
Why?
minus h
2a.
square by 2a. Potential energy is 0, right? So I am directly going to
Isha.
d2 psi, and it will, can be written in the form d2 psi by dx square equal to 2m e by h cut square psi, and negative sign is there. Okay. Now what is they are saying is show that there is no acceptable solution for this Schrodinger equation when E equals to 0. So one thing is definitely, yeah, Arunotpal, when asked the question in the discussion forum, he said that E can't be 0 because if E is 0, then it is stationary, and that cannot be possible, right? If it is stationary,
Yeah,
then Heisenberg uncertainty principle cannot be fulfilled, or according to the Heisenberg, yeah,
it can't be
can't be right
addressed.
there. Okay, can't be addressed. So that's it. So we cannot really measure the means if it is in rest, that means the uncertainty in position is 0. That cannot be the case, right? So again, so E cannot be 0. Acha, the time is almost 7. You go, I will come. Okay, so we'll try to wrap it up. So suppose E is equal to 0, then mathematically what will happen? Let me also see. Huh? So suppose E is 0, so then d2 psi of dx square will be 0, right? If E is
Yeah.
0,
Hmm.
then psi doesn't really come d2 psi, and when we will solve it, it will be something like a plus bx if you check this, right? Suppose d2 psi by dx square, it is something like that. Then let us go from here only. The psi dash is d psi by dx. So this will be a plus, sorry, b, right?
B
And psi double derivative will be 0.
is
So
0.
that is
Hmm.
right. So it will be something of that form. Now let us, and what they are saying that yes, that stationary state, that we, means particularly stationary, that is all fine, but we try to solve it using the boundary conditions. If you read the
Yeah,
whole question.
it will not be normalizable then.
So the boundary
A
conditions are
plus.
psi of, suppose our length is a of that particle in a box. Is it infinite square wave? So it should be 0 at the boundaries, right?
Hmm.
So suppose now whatever we have done, so psi of 0 is what? A, right?
Yeah.
And a plus b into 0,
Hmm.
then it is a. And also psi of 0 is 0, so a is 0. And another psi of a is 0. Then psi of a is here, means a plus b into a is 0. Now a, we already know a is 0, right? So b into a is equal to 0, and a is a length, right? A can't be 0, so b is 0. So when the energy is 0, then what we have found?
Everything is 0.
Yeah, the psi is 0. Psi is 0 at everywhere,
Yeah.
Yeah.
which is again not possible. Means this is the trivial solution which is not possible, because that will not follow the boundary
You don't have a
condition.
system then.
Yeah, we don't have a system.
Yeah,
So
like
what
the
we are talking about
probability of finding particle is zero.
will be 0. Yeah. So that is one thing, right? So
Yeah.
we have proved the first thing, that E can't be 0 mathematically using the boundary condition. Now what if E is less than 0? So this we can write. Later, let me go to the next thing here. So d2 psi by, we are on the next slide actually. I have copy pasted it. Minus 2me by h cut square psi. Now when E is negative, then what we can understand,
Positive.
this is positive, right? So let us write in such a way, what we are writing it for all the things, that kappa square psi, where kappa square is minus 2me. E is negative. So when E is negative, suppose E, so kappa, what is the value of kappa? Kappa is minus 2me by h cut square. Now you can see that kappa can't be kappa here is not imaginary because E is negative, right? E is negative, negative, positive. The overall kappa will be positive.
Hmm.
So for these cases, the solution is the general solution is in the form a e to the power kappa x plus b e to the power minus kappa x. Right now, I am not going to that infinite boundary condition. Let us just try to get the general solution. Okay, from this will be a general solution. From here we can see that again we have that boundary condition psi of 0 is equal to psi of a is equal to should be 0, right? So now what are we getting at psi of 0? That is psi of 0 will be 0. Now that will be a e to the
Equal
power
to
0
A is
plus
equal to 0.
b to the power 0 is equal to 0. Then b is equal to minus a.
Hmm.
So psi we are getting something, if we take the a common, a to the power kappa x plus I minus e to the
Minus.
power kappa x minus kappa x, right?
Hmm.
We are getting something like this for now. Now when psi of a is equal to 0, it is also given, right? So it will be something like, now it will be a into e to the power kappa a plus suppose we already got it, right? And minus
A
e to the power kappa a
minus
minus kappa a, that is equal to
equal
0.
to 0.
Now a is
A cannot be 0.
a can be
A
a,
cannot be 0.
a cannot be 0. Why are you going to that a thing?
Because if A is 0, then B is also 0, then everything is 0.
That is going to that is going to happen. And that is going to happen. And that's
No,
what
I
I'm
am talking about capital A.
yeah, I am
Yeah.
also talking about capital A.
So
Why
B
this
is equal to minus A.
see
So
that see the when this acha, so we are arrived at this portion until this portion, okay. Until this portion there is no doubt, right? So the doubt will come, let me what where I have the doubt. So when this kappa is imaginary na, so when E is positive, so maximum is infinite well problem we have solved. So there E is actually positive, right? So we will see that eventually this kappa or k what we have taken there, that will be imaginary. That's why the that solution is uh, actually different. When we went for infinite potential solution, we go for like this d2x square minus kappa square psi. So such a way that then kappa is 2me by h car. We don't want our k or kappa whatever we are assuming to be negative. For that we got that general solution a sin x plus b cos x, something like that. Cos k. I'm not going to there. I'm just saying that doubt might come that acha, let us oh, I have produced a doubt on your mind right now. Acha, let me come to this problem only. So suppose this can be possible when either a is 0 or e to the power kappa a minus e to the power minus kappa a is 0. So
yeah,
that means it will eventually mean that e to the power kappa a is equal to e to the power minus kappa a, and when we multiply we get 2 kappa a is equal to 1, and that will lead us to, since I am just now taking this thing here,
kappa equal to 0.
so take ln of both the things. So 2 kappa a, taking ln
It is
at
0.
both the sides, it will be 0. Now we'll find a can't be 0, so kappa is 0. And when kappa can be 0, m can't be 0, h is not 0, so then e is
E
0.
is 0.
But we already took e is negative, right? We are solving this for e is equal to negative,
Hmm.
Yeah.
so kappa can be 0. So this whatever we are discussing here, that e to the power kappa a minus e to the power minus kappa a can't be 0. Okay, so a is equal to 0 to satisfy this thing. Now as a is 0, then b is 0. Now again we are reaching the same, that psi is 0. So So that is what they are saying, that show there is no acceptable solution to the time independent Schrodinger equation for the infinite where E is equal to 0 or E is less than equals to 0.
Both the cases.
Yes. When we will go for E greater than 0, then our solution is altogether different. It will be something in trigonometric thing, or you can write it in the terms of exponential thing. But there our k is different, k or kappa.
Yeah.
So for that purpose, we will get that yes, that is possible. That solution. So the doubt what I was asking, I was also thinking that suppose this is also a general solution, right? For what we used to do, ikx plus b to the power minus ik or kappa. Okay, here kappa is different. Here kappa is 2me by h cut square. Here the kappa is different, or kappa square kappa. Here the minus is there. Oh, so there is some difference due to that. I am not yet able to fully grasp that. When I will take that, I will tell you. Means
Yes, like first, before taking a e to the power kx plus b e to the power minus kx, I was also thinking about that.
hmm.
But my doubt was if it is possible to consider imaginary value of kappa in that
Hmm.
solution you wrote on top.
Yes, you have
But
also written like that there, right?
yeah, like, but for that, if we get a negative angular frequency inside sine or cos, so that will lead to hyperbolic functions. So I was
Yeah.
not sure
Yes. Actually, yes.
if hyperbolic functions are acceptable for
No, they are not. They
sine.
are not actually. If you, I think one of the, in one of the solution manual, it was also solved it like that way, that using hyperbolic, cos hyperbolic and sine hyperbolic. Actually, I don't really know the hyperbolic function. That's why I didn't go into that way. Actually, that's why I tried to solve it in a simpler manner. So it is something like that. That when E is equal to 0 and E less than equals to 0. So it is the case is something like that. We will not, the psi will be 0 everywhere. So that can't be the case. We cannot really satisfy the boundary condition, or even if it means using the boundary conditions, we are getting psi equals to 0.
Okay.
Okay. So let us wrap our session here. So I am going for a
Uh,
class right now.
can you just
Yes.
stop the recording? And can I
Yes.
share my screen?
Yeah,
Just
sure.
quickly.
Let me